In this video, I'm going to briefly review the moment of inertia transformation equations. I'm going to show you those equations, and then we're going to work an example using the equations where we basically take a shape, and we've already calculated its Ix, its Iy, and its product of inertia, Ixy. And then we're going to use those transformation equations to calculate I about a set of rotated axes from the original set of axes. There's two kinds of calculations that we ultimately want to do. So given an original Ix, Iy, and Ixy, one of the calculations we want to do is to find the Imax and the Imin and the angle at which that occurs. The other is to basically find I about Ix prime and Iy prime about an arbitrary set of axes at some arbitrary angle. So those are really the two calculations. And we're going to use equations to do that. And we're going to use Mohr circle to do that. In our class, we really emphasize Mohr circle more than the equations. But Mohr circle is based on the equations. And for completeness, I'm just putting a couple examples here about the transformation equations that in later videos I will flesh out. But for now, I'm just going to put a minimum number of videos there just to expose you to them before we get to Mohr circle. But it's really the same thing. We're using the equations or we're using Mohr circle. Mohr circle is derived from the equations. So for completeness, I just wanted to show you the equations. And as a bonus, I'm going to show you an Excel spreadsheet that I've created that makes calculating the equations easier. And certainly it helps you check your calculations as well. In your folder on MOI transformation equations, which is on the OneDrive and also on the website, there's three documents we're going to talk through in this video. One is basically a summary of the transformation equations. And there's one set that are in terms of sine squared and cosine squared theta. There's another set that are in terms of cosine 2 theta and sine 2 theta. They're basically the same equations. We just did a trig transformation to convert the cosine squared terms to the cosine 2 theta terms. And the second set, the cosine 2 theta, sine 2 theta, are slightly easier to calculate with. I'm going to show you both sets of equations. This is the Imax or Imin calculation. And then this is the angle theta 2p, or 2 theta p, that we use to find the orientation of the principal for the Imax values. So this is a review of the equations. If you go back to the derivations, and I'm not going to go through it completely here, I'm just going to point out a couple key things again. So again, for an arbitrary area, we defined a dA, we defined an x and a y in terms of angle theta, or in terms of angle alpha. We rotated this axis, these axes, some theta. We defined an x prime and a y prime. We wrote x prime and y prime in terms of r, alpha, and theta. We did a trig substitution using difference angle identities. And ultimately, we got x prime and y prime in terms of x, y, and theta. So we got rid of r and we got rid of alpha. And so then once we did that, then our I about the rotated set of axes, like our Ix, our Ix prime, is just our definition of moment of inertia, is the integral over the area of y prime squared dA. And so we take this y prime and square him, and you're left with these three different terms. Keep in mind theta is known, so we can bring the theta terms outside of the integrals. And so once we squared this y prime, we got a y squared dA integral, which is Ix. we got a x squared dA integral, which is Iy, and then this integral of xy dA integral showed up, and that's our Ixy, or our product of inertia. And so we did this a couple classes ago to just show you that why we care about product of inertia. It showed up when we did this derivation. And so that leads to this equation for, which I call the cosine squared, sine squared equation, or Ix prime at some angle theta. You could do the same derivation for Iy prime, and you get a similar equation. And you could do it one more time for the product of inertia about those rotated axes, and you get a product of inertia equation. So we're going to use these today as equations, and then these actually form the basis of our Mohr circle as well. Basically, if you sub in angle identities, you get these forms of the equations, where this is an I average, this is an Ix minus Iy over 2, this is a cosine 2 theta, and this is a sine 2 theta term. Same equation, we've just used trig identities to put them in terms of 2 theta terms. And these are actually easier to calculate with, and we're also going to use these to derive Mohr circle. So pay attention. So here's an example problem. This particular problem, I repeat the equations here. These are the cosine squared, sine squared form of the equations. These are the cosine 2 theta and sine 2 theta form of the equations. So we have this S shape here, and I'm not determining the Ix and Iy and Ixy now. We've done that in previous examples. But if you did that, I didn't even give the dimensions here, but that's okay. So for this particular S, Ix is 15.7 inches to the fourth, Iy is 1.04, and Ixy is a positive 2.68 inches to the fourth. So think about that. This S shape lies mostly along a diagonal that goes from quadrant 1 to quadrant 3. So you would expect that shape to have a positive Ixy, and it is positive. The other thing you notice about this shape is more of the area is closer to the y-axis, and it's farther from the x-axis. So you'd expect the Iy to be larger, and you would expect you would expect the Iy to be smaller, and you would expect the Ix to be larger. And that's the true. So Ix is 15.7, it's large. Iy is 1.04 because of the area so close to the y-axis. And Ixy is positive because it lies in quadrants 1 and 3, as you would expect. So basically, we want to take those values of Ix, Iy, and Ixy about our standard horizontal and vertical Cartesian coordinate system. And we want to find IU and IV about a rotated set of axes. And so IU is at 15 degrees, and IV is 90 degrees from that. You could also call this X prime and Iy prime. You could call this I theta and I theta plus 90. So I use those different terminologies or different notations kind of interchangeably. So we're going to use two sets of equations to do it. I'm going to go ahead and calculate an I average. And so I average is 15.7 plus 1.04 divided by 2. So that's 8.39. And then we'll calculate an Ix minus Iy over 2, and that's 7.35. And again, we'll use these later. These are intermediate calculations. So let's find this I15 right here. So first of all, we're just going to use the cosine squared equation. And we're going to plug in the Ix, the Iy, the Ixy, and 15 degrees. So I15 is 15.7 cosine squared, 15 degrees, plus IY, which is 1.04, sine squared, 15 degrees, minus 2, and this 2.68 is IXY, sine 15, cosine 15. And we find I at 15 is 13.4. The product of inertia at that orientation, we're going to use, I'm actually going to use the 2 theta equation here because it's easier. See, so our angle is 15 degrees, but 2 theta is 30. And so if you actually look at equation 2c, it's this guy right here. So it's Ix minus Iy over 2, which is 7.35. 7.35 sine of 30 plus IXY, which is 2.68, cosine of 2 theta, which is 30. And we get IUV at that rotated system is 6 at 15 degrees. Finally, the I at y prime, or the IV, or you can also call it I105. You basically take 15 degrees plus 90, you get 105. And so we can actually take our, first of all, we can use the IV equation, or we can just simply take the same IU equation and just plug in 105 into it. And if you know what you're doing, you've got multiple options. I think I took the first equation and put 105 into it. And so if you take that first equation, put 105 into it, you got Ix cosine squared 105 plus Iy sine squared 105 minus 2 Ixy sine of 105 cosine 105, and you get 3.36. If you take the second equation, this 1b, and plug in 15 degrees in him and everything else, so this is the Iy prime equation, you also get 3.36. So you actually have 2 different choices of getting the I at the IV value. So those are using basically the cosine and sine squared equations. To use the 2 theta equations, these are actually slightly easier to calculate in your calculator because you don't have to square the cosine squared term. So that's like extra steps in your calculator. So we already calculated I average is 8.39, and we calculated this Ix minus Iy over 2 term, which is 7.35. And remember the equations we're using are these. And by doing these I average and Ix minus Iy over 2, these make the equations even easier to deal with. Remember, these are 2 theta equations. So even though we're looking for the calculations at 15 degrees, the equations use 2 theta just because of the trig identity. And so we're going to plug in 30 degrees into the equations. So I at 15 degrees is I average, which is 8.39, plus the second term, which is 7.35, cosine 2 theta, which is cosine 30, minus Ixy sine 30, or sine of 2 theta. And we get I15 is 13.4, which is what we got before. The IV equation, which is 90 degrees from that, is this equation here. Again, our I average is there. Our Ix minus I over 2 is there. We subtract this. So the signs flip. This is a flip sign, and this is a flip sign. Otherwise, the equations are very similar. And so at V, we got 3.36, which is what we got before. And then finally, our product of inertia in that 15 degree or coordinate system is 6, like we got earlier. So this is an example of using both forms of the transformation equations, given an Ix, an Iy, and an Ixy at an original coordinate system, to basically find IU, IV, and IUV at a rotated set of axes. Just for kicks, I also sent you a Excel spreadsheet that does this.